In today's lesson, we are going to be looking at the sum of squares. Now, the sum of squares is more previously known as the Pythagorean theorem, which you may have heard of before. But it's also known as the sum of squares, and the reason is because Pythagoras, a Greek mathematician, while is kind of the popular name for it, he wasn't the first one to actually come up with it, right? So Indian and I believe Asian mathematicians before Pythagoras, many years before Pythagoras, had been looking at this concept. Pythagoras is the one that kind of maybe fine-tuned it or attribute or put his name on it, which is what we used to call it quite a bit. But we're just kind of changing it to sum of squares just to recognize the fact that it wasn't just Pythagoras who came up with this, even though he is largely credited with it. There were definitely other mathematicians, other cultures working on this same concept well before his time. And if you want, you can take a look at looking at some YouTube videos. Definitely take a look at who Pythagoras was. He's kind of an interesting character. Definitely kind of started a math cult, so to speak, and has had some interesting thoughts, weird thoughts, kind of strong opinions on fava beans. You heard that right, fava beans, like the vegetable or the legume. I guess a more technical term. But yeah, interesting character. Good contributions to math, but definitely interesting character. Weird character. But we're going to look at the sum of squares theorem, or the Pythagorean theorem. And what it states is that it states that the square of the hypotenuse is equal to the sum of squares of the legs. Now you might be thinking, what the heck does that mean? Well, this is specifically for a right-angled triangle. So we have a right-angled triangle here, and we want to label these three sides. Generally speaking, we would label this A, B, and C. Right? C is always going to be this longest side. And these sides have specific names. Right? C, the longest side, is called our hypotenuse. So when we're talking that hypotenuse that we just mentioned, that's referring to C, the longest side. A and B, these are what we consider the legs of our triangle. So the square of the hypotenuse is equal to the sum of squares of the legs. And what that formula is going to look like, it's going to look like a squared plus b squared equals c squared. So when we talk about this formula, when we talk about the squares, we're talking about squaring the side lengths. The side length a squared plus the side length b squared is going to equal the side length c squared. Now, what does that actually mean? What does that look like? Or what's one of the ways they kind of confirm this? And one of the ways they confirmed it is by actually making squares off of each side. So if I look at A, if I make a square based off of that side, right? So a square of equal length, right? Sides of equal length. So it's A. I could call it A squared, right? The area of this shape, A squared. If I look at B, making a square off of side B, this would have an area of B squared, or B times B. And if I were to add these two areas up, it would equal the area of this larger square made off of the hypotenuse, or C squared. Right? So if I take the square of one plus the square of one leg plus the square made off another leg, it will equal the squared off of the hypotenuse. So again, another way that we can kind of come up with the proof for it. So the a squared plus b squared equals c squared. And if you want to see a visual demonstration of this, just go to YouTube, type in Pythagorean theorem demonstration or water demonstration, and you'll see basically the water from the large square based off the hypotenuse. Right? So again, this was our hypotenuse. Again, I'm not going to play the video here. I don't know if there's any copyright issues or anything like that. But this c squared, when you rotate the wheel, the water pours down, it fills up a squared and b squared perfectly. And then when you rotate it again, the water from these two squares, a squared and b squared, fill up the c squared square perfectly. Right? So again, just a visual demonstration of how those areas are related and where this kind of theorem comes from. So let's use this theorem. We're going to use it to find these dimensions, or we're going to use it to find lengths of our triangle, specifically a right angle triangle. Right, so the dimensions of a computer screen are 36 centimeters by 27 centimeters. So we see 36 by 27. We want to determine the length of the diagonal of the computer screen. I'm going to put a little right angle in there on each corner just so we're aware, right? But rectangles have right angles, so we should be aware of that anyways. Now, the diagonal is important because that is how we actually measure the size of screens, right? So when you hear of like a 32-inch screen, a 32-inch monitor for computers, we're actually measuring the diagonal, right? If you go and measure the length or the width, it's not going to be what it's advertised as. That's because they're measuring the diagonal. And we'll look at this and we'll see why they kind of do that. So I have my triangle. I need to label my A, my B, and my C. Well, the diameter, or the diagonal, sorry, the diagonal, not diameter. The diagonal is actually my C because it's the hypotenuse. And then A and B, my two legs, it doesn't really matter which one's which. So I'm just going to say A and B. Again, like I said, it doesn't really matter. And I'm going to write out my formula. So A squared plus B squared equals C squared. So A is 36. So 36 squared plus B squared, which is 27. So 27 squared equals C squared. Or I can just write it as D squared. Keep the notation similar to my diagram. I'm going to square each term. So 36 times 36 is 1,296. Make sure you're squaring it and not multiplying it by 2. That's a common mistake that people do. They multiply it by 2. They don't square it. Remember, squared means the number times itself. And plus 27 squared is 729, and that equals D squared. I can add up my two values and get 2,025 equals D squared. So based on what we kind of did in the last example, looking at these ones with the squares, I've found the area of what the square would be if we imagine, just bear with me, if we imagine it coming off of this hypotenuse, right, I found that area. Right, or I guess based on our diagram, it probably makes more sense to say this square. I found that area off of that side length, if that was a square. But I don't want that area. I want the side length. Another thing you could do is you could look at it and say, you know what? That is very large compared to my other sides. My two sides are 36 and 27. And I'm going to say that my diagonal is 2,025. Seems a bit high. And it is, because we have one more step to do. And this is going to be the same in this example and the next. The last step we should be doing with the sum of squares theorem or Pythagorean theorem is I want D by itself. So if I want D by itself, I have to get rid of this squared. Right? How do I get rid of squared? What's the opposite of squaring something? Well, the opposite of squaring something is square rooting. So if I move that square over, or you could think of canceling it out by square rooting and then doing the same thing to the other side, I'm going to take the square root of 2,025, and that will give me my diagonal. And that then when I do that calculation, I get 45 centimeters is equal to my diagonal. So we can see, based on what we have for our diagonal, it makes sense that we would measure screens based off the diagonal rather than the other two, the leg and both legs, right? And if you look at the measurements, the diagonal is going to be the largest one, right? So I'd rather call this screen a 45 centimeter screen rather than a 36 centimeter screen or a 27 centimeter screen, right? Because 45 is bigger. So it makes me feel like I'm getting a larger screen. So that's why they kind of look at the diagonal rather than the length or the width. Example 2 is similar. We're still going to use the Pythagorean theorem. We're dealing with a right angled triangle. However, here we're told that the height of the sail of a sailboat is 15 meters, and the hypotenuse, or the diagonal, is 17 meters. And we want to determine the area of the sail. So this is important because reading the question, we want to find the area of the sail. We don't want to find anything else. We want to find the area. Right? So the area formula for a triangle is base times height divided by 2. I have my height, 15, but I don't have my base. I have the hypotenuse, but that's not the base. So I need to find the hypotenuse, and that's where the Pythagorean theorem, or the sum of squares, comes into play. So we're going to have 2 steps. The second step is going to be using the area formula. The first step, I need to find, we're going to call it B. So if we label these sides, our hypotenuse is going to be C. We'll call this A, and we'll call this B. You could switch it around and say that I'm looking for A and I have B. It's going to be the same formula, just the variables are going to be in slightly different spots. Now, we're going to plug it into our formula. So A squared plus B squared equals C squared, right? That's our sum of squares formula. I'm going to plug in the values that I know. So A is 15, so 15 squared plus B squared I'm going to leave because I don't know what it is. And it's going to equal 17 squared. I'm going to expand or kind of simplify my exponents. So 15 squared is 225 plus B squared I'm going to leave because I can't do anything with that. And 17 squared is 289. Okay, I've used my exponents. I have values now, and I'm looking for B, or B squared. So I'm going to start to solve this equation. So I want to move everything away from the B squared. So I'm going to move the minus 25, or the 225 over by taking away 225 from both sides. One side will cancel out. I'm left with B squared equals 64. All right, now I'm at a step where I can find my B value. The only thing left to do, I don't want B squared, I want B. So similar to the last example, we're going to take the square root of both of the one side, and I get B is equal to 8. Specifically 8 meters. So that tells me that the base of my triangle is 8. And now I have enough information to go through and find the area. I have my formula sheet. I have the base, which is 8. And I have the height, which is 15. So I'm going to multiply them, divide them by 2. 120 divided by 2, and I get 60 meters squared. So once I found the base using the sum of squares, or Pythagorean theorem, I can now plug that into my area formula to find the area of this triangle. So that might be something you have to do, and that is something that we're going to do going forward, is going to be incorporating the sum of squares theorem into some of our perimeter or area or other measurement type questions, where maybe we're given some information and forced to find either the hypotenuse or one of the legs to then use in another formula. But again, the main thing is just making sure we know what the sum of squares theorem is, the A squared plus B squared equals C squared, and knowing how to use it. And these are the 2 ways that we can use it, either by finding the hypotenuse or by finding one of the legs.